space by itself and time by itself cease to exist in isolation, and instead there is a single unified framework that we call space-time. What this means is that we live in a four-dimensional universe. When I move through space, this dictates how quickly I move through time. The faster you go in space, as you get faster and faster and faster moving through space, your rate of progression into the future slows down. So you literally advance into the future at a slower pace the faster you are going in space, and then vice versa.
Right. Hey, man.
Hey.
Right, if you keep that about a fist from you, right?
Yep, here we go.
You have no idea how excited I am by this, by the way. Somebody once asked me, they're like, whoa, if you could interview anyone, and I was like, there's three. There's Axl Rose. Do you know Jurgen Kloppers?
No clue.
He was a manager of Liverpool Football Club.
Oh, okay.
And then I said, this guy, Paul Sutter.
This guy, everyone's like, who?
This
I got the
spaceman.
first two names, but what's the third?
I was like, I've listened to so many of his podcast episodes. I've played the Relativity one. Was that part 1 and 2, episode 14?
Yep. That was way back in the
Yeah.
day. Yeah, that's a deep cut right there.
I found you early on, man, and I've played that to because I told you I watched Interstellar with my daughter.
Oh yeah. Interstellar is a fantastic movie. I do really love that movie.
Can you explain the end?
Love is the fifth force of nature.
Oh man! So watching that with my daughter, we must have paused it 20 times, and then we got to points I was like, I can't explain this, but I've got a podcast. So we were
But I've got a guy.
There's this guy. He's a spaceman. You can ask him questions, even if you're a princess. I don't know if you remember, there was that girl who asked a question. She's like, she wants to be a scientist and a princess.
Oh, that's right. I do remember that. Oh my gosh. I hope both dreams came true for her.
I hope for her they did. But I said to my daughter, I said, this is the guy. And so we're listening to it, and I was struggling with time dilation on it.
Yeah.
And that's when I emailed you, and you were like, yeah, sure, man.
Of course.
Here we are.
You
had a good time in London?
I've had a fantastic time. I spent all day yesterday at the British Museum because I'm a history nerd. I love just artifacts, stuff. I could spend hours and hours and hours in a museum. I really could.
Well, I'm a space nerd, but I don't get it. I've got so many questions for you, man.
I was peeking at the list.
Well,
I feel like I'm being interviewed for my PhD exam again.
There's stuff I don't understand that I want to understand. And also stuff I think about late at night. I get like just weird and start thinking about things. The stuff that you probably think about.
As one does.
Can we start on special relativity?
That's a good place to start. It's a good place.
Actually, there's probably a better place to start. I was in the car on the way, and I was listening to an podcast by a guy called Jesse Michaels, and he was talking about simulation theory, which we can talk about.
Yeah, we can get into that.
But what he was talking about is the absolute perfect laws of physics that enables everything to exist. The fact that we're sat here for life to exist, for the universe to exist, for everything to work, are so specific that on so many different metrics, if things were slightly out, the universe wouldn't work.
Yeah, this weird fine-tuning that we see in the universe, that if you change the charge on the electron, the speed of light, the strength of gravity, if you take any of these parameters, like basic facts about the universe, and change them, then our kind of life that we know it, which is the only kind of life that we know, isn't just difficult, but absolutely impossible. Like stars never form in the first place, or atoms never bind together in the first place, and then it's all over. And that's a deep and open mystery of why is the universe the way it is. Scientists are not the first people to ever ask that kind of question. This is a long intellectual tradition stretching back thousands of years, but it's still a question that resonates and is relevant today.
What does it make you think?
So I feel like I'm going to say this a lot during this interview. And it's something that I encourage my fellow scientists to say as much as possible when they interact with the media or they sit on podcasts or they talk. I don't know. I don't have an answer to that question. And there is a value in not knowing. There is a joy and freedom in not knowing. There is a certain a beauty in ignorance. One, because it means job security. Like I get to keep trying to answer these kinds of questions as a part of my professional career and explaining our attempts to answer them as a part of my professional career. But also, I don't know. I don't have an answer. At least not a good one, or one that I have no answer that at the end of the day, I sit there and think, okay, I think that's it, even though I have no evidence for it. But like, I think I know why the universe is the way it is. I don't know. This is a deep, like, people much smarter than me, going back thousands of years, have attempted to wrestle with this question, and they haven't come up with any good answers. And we can talk about the potential answers, and it's fun to explore all the corners of a question like that. But at the end of the day, we have no good answer for it.
Just a guess, just a thesis.
Not even a thesis, a hypothesis, not even that, not even a hypothesis. We just have guesses when it comes to questions like that.
Well, let's start with special relativity.
Let's start.
Because that's where it really started for me, that part 1 and 2 episode. I think it's episodes 14 and 15. The ones I made my girlfriend listen to yesterday.
I'm sorry.
No, she enjoyed it.
Oh, okay.
Yeah, so
okay. Usually that's like a deal breaker in a relationship, is forcing people to listen to my episodes, but
well, so we had a fair split on the journey. It was half Taylor Swift,
okay,
half Paul M. Sutter.
You know what? That's fair.
It's a good mix.
The two sides of the same coin.
It's an unusual mix. But I've made my daughter listen to it. I've made my son listen to it. I made my old producer listen to it.
This is why you have no family anymore.
I've got no friends left either.
This is amazing.
No, because
I'm the only one left. That's why you brought me out here.
But the one thing that gets everybody was length.
Yeah.
That length is relative. And so you had that explanation of the garage. That you can have a 7-foot garage and an 8-foot car can fit inside it.
Yep. It happens. It's a thing. It's a real thing. And we know this is a thing, not because we've measured cars moving through garages, but length contraction is a real facet of our universe. And this was completely unexpected prior to Einstein, prior to the development of special relativity. We had no clue that the universe would act this way, but we know that it does. And one of my favorite examples is the muon. So the muon is a fundamental particle.
Yep.
It's related to the electron. It has the same charge, same spin, but it's a little bit heavier. Because it's heavier, it has a very limited lifespan. It will only live roughly
2 seconds.
like 2 microseconds.
2 microseconds.
Yeah, like that. It's gone. So if you create a muon, a couple microseconds later, it's gone. So we know that muons are produced in our upper atmosphere. When cosmic rays slam into air molecules, it creates a shower of particles, it creates some muons. These muons stream down to the ground. And in fact, you can build detectors on the ground that can see these muons. You can even go to the hardware store, no joke, and build yourself a detector that can see muons. These muons don't have enough time to go from the upper atmosphere to the ground. They're limited by the speed of light. They only have 2 microseconds to live. That's not enough time to travel that 100 miles or so from the upper atmosphere to the ground. The only way muons can make it to the ground is if, because they are traveling so quickly, the distance between the upper atmosphere and the ground from their perspective is shorter because of that length contraction in our universe. So to them, to this traveling muon that's going nearly the speed of light, it doesn't have 100 miles to go. It has only like a mile to go, or even less, depending on its speed. And so it can make it in plenty of time. And then it dies.
Okay. So the fabric of space-time.
Mm-hmm. Mm-hmm.
I've heard you explain it.
Yep. I feel like you're about to hear me explain it again.
Yeah. Well, I think we should for everybody else, because that's where I'm going to have questions. Let's go back a touch. Let's go. Can you explain how Einstein kind of came up with special relativity? What was the process he went through? How did we get them? Then what did that fundamentally change about our understanding of our place in the universe?
Yeah. This is very important. For one, Einstein was a genius of a different kind. he had trouble explaining how he came up with his ideas. We know, based on what he would say and his writings, that he was incredibly imaginative, that he could envision scenarios and just think deeply about a certain mental picture. And then some mystery happens and he comes out with a brilliant mathematical insight or physical insight. So to explain Einstein's thought process is literally beyond me, because even Einstein himself couldn't explain it. He's like, I don't know, I thought about it. Like that's as far as it would get. But in the case of relativity, we do have a little clue. As a kid, as a teenager, most teenagers are not thinking about subjects like this, but Einstein is. Einstein imagined what it would be like to race a beam of light. Like if you turned on a flashlight and then he started on a bicycle. He didn't have jet engines or anything accessible to him to imagine. So you imagine if you rode on a bicycle next to a beam of light and you pedaled as hard as you could and you caught up to the beam of light. You were able to travel at the speed of light, and you looked over at that beam of light next to you and you were traveling, you were keeping pace with it. What would you see? This is the question that teenage Einstein asked himself. He wouldn't be able to answer it for another decade. It wasn't until his 20s that he came up with an answer. And the answer to the question, what would you see if you caught up to a beam of light and you looked over? The answer is you can't. You can't catch up to a beam of light. That was his answer. It turns out you can't, that you can't envision what's going to happen because you can't. It's impossible. You can't catch up to the speed of light. Einstein realized this because he was a very ardent and devout student of Maxwell. Mm-hmm. James Clerk Maxwell, another genius living in the mid-1800s, a Scottish physicist and mathematician. He is the guy who gave us our theory of electromagnetism. He realized that electricity, magnetism, and radiation were all unified together into a single theory. This was a major advance in science and a major advance in our understanding of the universe. Through this theory, Maxwell discovered that light, the light that surrounds us right now, is made of electromagnetic waves of electricity and magnetism that feed off of each other and travel through space. And that theory said very plainly that light travels at a fixed speed. It just goes this fast, whatever units you want to use. That's it. There's no plus or minus to that. It doesn't depend on perspective. The speed of light is the speed of light.
Whether you're traveling towards it or away from it.
Exactly.
Can't get my head around that one.
So if I'm chasing you, and I shine a flashlight at you, the light leaves me at the speed of light. Not any greater, not any less. It just leaves me at the speed of light. You turn around and you see that light rushing towards you. That light approaches you at the speed of light, not any more or any less, regardless of how fast we're going. If I were to instead throw a ball at you and I'm chasing after you, the speed of the ball is my speed plus whatever speed I can give it by throwing it. I get to add those velocities together, but not with light. Light, it does its own thing. And this is why Einstein realized that it's impossible to catch up to a beam of light. It's because Maxwell's equations plainly said that light always travels at that speed regardless of your perspective. And that if you were to look at that beam of light, you would see waves of electricity and magnetism frozen in place, which doesn't happen. That is impossible according to the equations of Maxwell. And so Einstein realized that there was this massive contradiction where Maxwell said one thing about the universe, like the speed of light is always the speed of light. And then Newton said another. Isaac Newton, laws of motion, basic stuff, fundamental physics stuff, said, no. You can add and subtract velocities. It does depend on your frame. You should be able to do this. These stories were incompatible. And Einstein had to pick Newton or Maxwell. He chose Maxwell and he was right. And from there, Einstein was able to develop the special theory of relativity.
Right. Okay. So what does that actually mean for us then? What did that change about our understanding of the universe?
So one of the it is a lot.
Yeah.
There's a long list of things that relativity informs about our universe. One thing is the equivalence of mass and energy. When we say his famous equation E equals mc squared, that's energy equals mass times the speed of light squared. The speed of light squared, that's just a unit conversion that tells you how much mass is a little bit of mass has in terms of energy and vice versa. You can drop that. You can ignore that when you're picturing this equation. Mm-hmm. The core of that equation is E equals m. Energy equals mass. Energy is mass. Mass is energy. These are two sides of the same coin. When we say an object, this glass of water, has mass, it really means it has an incredible amount of energy compacted inside of it. And if I look at something that has just energy, like kinetic energy or heat energy, this also has mass. It means that a warm cup of coffee weighs more, literally weighs more than a cold cup of coffee because it has more energy. Therefore, it has more mass. This unlocks all of nuclear physics, forms the basis, one of the bases for quantum mechanics. This is how we understand a lot of things in quantum mechanics. And that's just one corner of special relativity. That is one outgrowth of this realization. The other major outgrowth is the unification of space and time.
Yes.
Where,
here we go.
Yeah, where we... prior to Einstein, prior to relativity, Einstein was not the only one working in the direction of relativity. We strongly suspect that in an alternate universe where Einstein never lived, other people would have put these pieces together and created a theory of relativity. That's not true with general relativity. Einstein was singular in that respect and a few other things that he did. But when it comes to relativity, there were lots of people right around the turn of the 20th century that were poking at this from different directions. And a lot of people came very, very close to him. He just did it first. And in this theory of relativity, we no longer have separate conceptions of space and time, which is our normal human intuition. Like, we have space. I can walk around this room. I can travel to London. I can go from one place to another. I move myself in space. And then I have this separate conception of time, where there's the past that I remember, there's the present that's happening right now, and there's the future that's about to be. And I'm traveling from the past into the future, and so is everything else. And that these two aspects of our universe are just separate aspects of a universe. There's just space and there's just time. They're just two qualities of our universe. With relativity, we find that it is impossible to talk about one without simultaneously talking about the other, where movement through one tells us, informs us, and is linked to movement through the other. So it was actually Einstein's former teacher, Hermann Minkowski, who laid out this framework that we call space-time, where space by itself and time by itself cease to exist in isolation, and instead there is a single unified framework that we call space-time. What this means is that we live in a four-dimensional universe. If you ever ask, like, is there an extra dimension? Yes, we call it time. It's already there. And that when I move through space, this dictates how quickly I move through time, and vice versa. You can't have one without the other. And what we have found through this unification, among many other things, is that the faster you go in space, the slower you go in time. That as you approach the speed of light, these effects really only show up once you're going really, really fast, like 90% of the speed of light or something like that. The faster you go in space, as you get faster and faster and faster moving through space, your rate of progression into the future slows down. And that when you slow down in space, if you come to a standstill, your rate of progression into the future, your rate of progression through time speeds up. It turns out every object in the universe is moving through space-time, through this four-dimensional universe at the speed of light. It's one way to think about it. And that the more you go in space, that has to cost something, that comes from something, that comes from your speed through time. So you literally advance into the future at a slower pace, the faster you are going in space, and then vice versa.
Okay.
Yeah.
Okay.
What a way to start.
Yeah, no. So this
for
is
the 5 people remaining.
There'll be lots listening. Okay. So this is where it gets.
This is heavy stuff. This is heavy stuff.
But I mean, we don't really experience that because none of us are really going. We're not really traveling fast through space.
Which is why Newton didn't know about this, why Maxwell didn't know about this, like Aristotle didn't know about this. We didn't know about this because these, at normal everyday speeds, which is normal everyday speeds, you're never going to notice these slight differences in progression through time versus progression through space. You're never going to measure it, but we actually have the capabilities to directly measure this because we have ultra precise atomic clocks.
And we need it for satellites.
Absolutely. Yeah. So if a lot of people ask me, how do we know that relativity is true? How do we test this? We're testing it every single day. You are a living testbed of relativity because our GPS satellites, in order to get GPS to work, it relies on incredibly precise timing. And the signals from the GPS satellites constantly beam out their current time. They're reading on their internal clocks. And then your phone compares the signals from different satellites and finds the little differences and figures out the distances and triangulates a position. There's wonderful engineering behind that. In order to get the calculations correct, to make sure that the GPS gives you an accurate location, it must take into account the speed of the satellite in orbit around the Earth, which is tens of thousands of miles per hour. Slow compared to the speed of light, but enough to matter for these kinds of precision calculations. If we didn't know relativity, we could still build GPS satellites, but they'd either be wrong or they would have a much wider uncertainty than they do. Your location would not be as precise. To get that precise location, to get that accurate location, the satellite must fold in the effects of special relativity, knowing that because that satellite is moving so quickly, its rate of progression, the ticks on its clock, are not 1 second long. They're a little longer than a second because it's moving so quickly.
Through space.
Through space, exactly, which is slowing down its progression in time, which means every tick on its internal clock takes a little bit longer than the tick on the clock on my wristwatch. And it has to account for that to get that precision in GPS.
So this makes time itself really weird.
Yeah.
Like a really weird, because as a kid, time is a clock.
Time is a clock.
And time is the same for everybody.
Exactly.
And that's what we believe. Time is just this universal thing.
Time is time. Yeah. And that's what Newton believed.
Yeah.
And that's what philosophers and scientists for millennia believed, that there is we call it like a master clock, like an imaginary clock sitting out in the universe that just ticks by. A second is a second. Everyone agrees. We all synchronize our watches in this room, and it's the same across the Earth. It's same across the Milky Way galaxy. It's the same across the universe. Everyone knows what time it is because we all advance at the same rate, and we all agree. Relativity destroys that. Absolutely destroys that. That synchronicity is a fiction. At best, it's something you can temporarily achieve when objects are close together. That no two clocks agree. That a clock on a rocket ship records a different time, a different interval of time, a different actual time than a clock sitting on the surface of the Earth.
So even driving a car at 100 miles an hour, does that, the most minute decimal change things?
Yeah. In principle, yes. It's something like a trillionth of a second, but it's there. It's not enough for us to notice in our everyday lives. It is enough for us to notice in GPS satellites. It is enough to notice in, say, like cruise missile timings. And it is enough to notice for our distant solar system probes and for particle accelerator experiments and all of this.
Because all of it is relative to everything is relative to our movement towards the speed of light. So is speed of light the constant?
Speed of light is the constant. It is the anchor that everyone can agree on, because the theory of relativity is exactly that. Like, your perspectives on the progression of time and the length of space depend on your perspective. They are relative to the observer. So different observers have different relative viewpoints on the ordering of events, the timing between events, the progression of history in the universe. But relativity doesn't throw everything out.
Mm-hmm.
Relativity does preserve some things. There are some things that are absolutely universal that all observers in the universe do agree on. And those are the laws of physics.
Mm-hmm.
That is what Einstein was able to cement. And one of those laws of physics is Maxwell's equations, which says that the speed of light travels at this speed, and all observers agree.
So the speed of light is almost the anchor to which everything in the universe is kind of anchored to.
Yeah, exactly. Yeah, we can all agree, no matter what. We could meet an alien civilization someday, and we could sit down and share notes and exchange recipes and all that. We will all agree on the speed of light. And that species could be traveling through the solar system at 90, blasting through on their warp drive. And as we exchange messages, we're both going to agree on the speed of light. Everyone can agree on that.
It still makes it really weird, though.
Yeah. Welcome to the universe.
Yeah. Well, it gets so then it gets super weird, because that's when I start thinking about Interstellar, and it makes me think time travel is possible in one direction.
As far as we know.
As far as we know, time travel is possible in one direction if you, because of the classic moment in Interstellar, he goes and sees his daughter who's older than him because of whatever happens in space. But
which was so beautifully and poignantly done in that movie. I love the art of that movie and how it explained this heavy physics concept that we're discussing in terms of people and aging and heartache and loss, very human emotions.
But that happens in space because of you experience time because you're moving at different speeds in space? What, because of gravity?
Yeah, so the time dilation that, what was his name, Cooper?
Yes.
In the movie experienced wasn't necessarily due to his fast motion through space. It was due to something else. It turns out there are two sources of time dilation, two ways to slow down a clock in the universe. One is by moving really quickly, and the other is by being near a strong gravitational source.
Okay.
If you're near strong gravity, your clock will run slower. That means here on the surface of the Earth, we are feeling strong gravity. We're feeling that pull of gravity. That the clock, the way our clocks tick here on the surface of the Earth is different than in the upper atmosphere.
Okay. And why is that? Is gravity itself changing time for us, or changing speed, or is it because it's changing speed?
The reason is it's accelerating us. So the key, the absolute key that unlocked relativity, general relativity, this is Einstein's theory of gravity, which is what happened was Einstein developed special relativity, and everyone recognized that this is major reshaping. Special relativity, it's almost like a meta theory of physics. It teaches us how to construct theories of physics.
Okay.
It teaches us that the fundamental relationships between space and time and energy and mass and momentum and all that. It teaches us how to construct that. And relativity, special relativity, is incompatible with Newton's theory of gravity. Because Newton's theory of gravity says, nope, there's a master clock ticking away. There's absolute rulers. Everyone agrees. We all know, when this mass changes, the force of gravity instantly changes all across the universe. Einstein looked at that and said, okay, I need a new theory of gravity, one that is compatible with our new understanding of the fabric of space-time, with energy and mass equivalence, with all this. It took him 7 years to develop the general theory of relativity. No one else was even close to approaching him in terms of the underlying framework. And the key insight to making general relativity work is that the pull of gravity that you and me are feeling in this room right now, it feels like our chairs are pushing up into us. That's what it feels like, because we imagine the gravity pulling us down, but what I actually experience is the force of the chair pushing up on my backside. You can imagine, let's say this studio, it's all closed off. The windows are closed. Let's put it inside of a rocket instead and put it in the middle of space. Okay, immediately we'd start floating around because we're in space. But let's say we ignite the engines, and those engines push the rocket. And those engines are underneath us, pushing away from us. It's going to push the floor up into the chair. It's going to push the chair up into us. We're going to feel that acceleration. Einstein realized that acceleration due to the rocket is identical to the acceleration of gravity. Not just similar, not just kind of the same, not just an analogy, but identical. Here in this closed room, there is no experiment that we could perform. Let's pretend we keep the windows closed, everything's sealed, we can't look outside. But inside this room, there's no experiment that we could perform that could tell us whether we are on the surface of the Earth or whether we are on a rocket accelerating at 9.8 meters per second squared. We could create a pendulum. It would behave the exact same. We could throw a ball, pass a ball back and forth to each other. It'd be the exact same. We could jump up and down. There's nothing we could do to tell these two kinds of accelerations apart, gravity and motion. So therefore, they must be the same because there's no way to tell them apart. This is the entirety of general relativity. That is the central postulate of general relativity, that acceleration is the same, whether it's due to rockets, whether it's due to gravity. So now this is how we get to time dilation. Moving clocks run slow. If I'm moving through the universe, my clock runs slower. If I'm accelerating through the universe, my clock runs slower because acceleration leads to movement. But acceleration due to a rocket is the exact same thing as acceleration due to gravity. They're the exact same thing. So accelerating clocks run slow. Clocks experiencing strong gravity run slow. It doesn't matter what's causing the acceleration, no matter what, the clocks run slower. One of the first tests of this happened, I believe, in the 1950s at Stanford, I think, where they shot a beam of light from the top of a clock tower down to the bottom, and they were able to measure a redshifting effect of the light due to its changing gravitational environment. And this is one of the earliest tests of general relativity. It's right there.
The humble bee, a keystone species crucial to the survival of Earth's inhabitants. Here's how things would look if bees vanished. And here's how they'd look if humans vanished. But imagine if instead we became a keystone species by doing things the right way, by taking responsibility for our actions and becoming the solution. Iron mines the world's most responsible currency the right way. Because the future depends on it.
So gravity is an accelerant.
Gravity is an accelerant.
And it's so strange because I always think of it the other way. I always thought of gravity as something that slows us down.
No, it's something that speeds you up.
Interesting. And so that's why, so when they talk about the Earth spinning, particular speed, I don't know what it is, some crazy fast speed. Yeah, fast speed. We're spinning, but we don't feel that because we're spinning with it. So when a rocket takes off from the Earth, it's still got that spin.
Exactly, which is why we like to launch rockets as close to the equator as possible, because when we launch the rockets from the equator, they start with that spin of the Earth, and so they get a low boost, so you don't have to work as hard to accelerate them to get them into orbit.
Okay, so is it from special relativity that Einstein discovered black holes, or mathematically proved black holes before we'd observed them?
It was as through general relativity.
Through general
It was
relativity.
through our understanding of gravity, and it wasn't Einstein.
Oh,
So it was another guy.
wow. I thought it was Einstein.
It was not Einstein. This is amazing. So Einstein created general relativity.
Uh-huh.
And I like to think of general relativity as a machine. It is a mathematical machine. It's obscenely complicated theory. It is. For decades, barely anyone worked on it because no one understood how to work through the mathematics. It's a set of 10 equations that are very complicated in isolation, and then they all interact with each other in various complicated ways. So what general relativity tells us, or teaches us, or enables us to do, is solve problems with gravity. And the general picture is that this space-time framework that we've identified in special relativity, this unification of space and time, is itself not rigid. It can bend and it can flex. And it bends and flex due to the presence of energy and mass. So what this means is that the raw presence of like a planet or a star or a galaxy bends space-time. And what we mean by that is that distances between two objects changes, whether they're out in the middle of nowhere or whether they're close to a planet. Like if you took a ruler and you said, this ruler is 1 meter long, and you brought it out in the middle of nowhere, you say, okay, this is a meter. Gotcha. You bring it close to the Earth, that meter is not a meter anymore. It's a little less than a meter because of the gravity of the Earth, because Earth is bending and changing those distances. And then it's also changing.
That's so weird.
It's so
weird.
weird. It's so weird and so beautiful and so much fun, which is the universe is far stranger than we could have possibly imagined. You know, we don't need science fiction here because the universe is weird enough. I mean, I love science fiction, but we don't need it, because the universe is weird enough on its own. Rulers do not stay the same. Clocks do not stay the same. And it depends on their gravitational environment. And then in turn, that bending tells objects how to move. So in regions where space-time is tightly curved, you can imagine sending like a beam of light down close to that well, and then it deflects, it bends around. This is how we identify our motion through the universe, is by following the bends and curves and the hills and valleys of space-time itself, which is four-dimensional and like impossible to visualize, but there it is. So Einstein developed general relativity. He developed this machinery. And he came up with a couple test cases. He was able to use it to explain something about the orbit of Mercury that had been a long-standing problem for centuries. Newton's gravity does not explain why the orbit of Mercury, it's a little bit off based on all of our calculations in Newton's gravity. It turns out, because it's so close to the sun, it has a slightly different space-time around it, and general relativity was able to account for that.
Okay.
Which is cool. And then that was pretty much it. That's all Einstein could do with his own theory. He crafted this theory. He knew it was internally consistent. He came up with a couple approximate solutions. And then he's like, okay, I guess that's it.
Done.
So there's this other guy, Carl Schwarzschild.
Okay.
Who was a mathematician and a physicist, very interested in relativity. Was in his 30s or 40s when World War I broke out, and volunteered to join the German army, serve his country, was in the trenches of World War I, reading Einstein's papers. Along with the shelling and the flooding and all the horrible conditions and the dying, he's sitting there reading. I think he was an artillery officer, if I remember right. And he's reading Einstein's papers. He comes up in the trenches with the first solution to relativity, the first application of relativity, and then he dies. because he contracts some horrible disease. But before he dies, he's able to send a letter to Einstein, and Einstein loves it, immediately recognizes how powerful Schwarzschild's solution is, and publishes it and shares it with the rest of the scientific community. So what Schwarzschild found was he took this machinery of relativity and he put it to its first useful application, which was, what is the gravity in the solar system? If I have a mass, say the sun, and it's perfectly spherically symmetric, it looks the same on the all side. I know it doesn't actually in reality, but like it's close enough. And I put a massive object there and I ask, wherever I go in the solar system, what does my gravity look like? What is my strength of gravity? Schwarzschild was able to figure out that solution, which Einstein himself wasn't able to figure out that solution, but Schwarzschild did. He came up with the first exact solution to Einstein's relativity, of which there are only, I think, 17 known exact solutions. Everything else is approximations or computer simulations. But Schwarzschild was able to write down with pencil and paper, this is exactly the gravity that you will expect around something like the sun. And this solution had some weird stuff in it. It had a weird feature where if you're looking at the gravity due to the sun or something like the sun, like another star or planet, whatever, in isolation, there's a special distance away from the center of that object. Very special distance that just behaved oddly in the mathematics, where if you're trying to like imagine a particle flowing from a great distance and then crossing that special distance, like it just kind of blows up. It gets very, very weird. Today, we call that distance the Schwarzschild radius in his honor. And physicists immediately picked up on this, as they were reading Schwarzschild's paper, like, oh, this is great. I know exactly what the gravity is going to be in the solar system around the sun due to the gravity of the sun. I have this machinery that I can write down. But what's happening at this weird distance? I don't know. The math just kind of blows up. As the decades go by, more and more physicists poke at this. And for, like I said, for decades, general relativity was this tiny corner of physics where like 3 people were working on it at a time. Most physicists at the time and still today were more interested in particle physics, in developing the standard model. They were running big experiments. Barely anybody was working on relativity. So progress was very, very slow. But people chipped away at this, and then they started asking some interesting questions like about this special radius, this Schwarzschild radius, this distance from the center. They said, well, what if I took something like the sun and I compressed it down? Like, let's say I took all that matter and I compressed it down to below that Schwarzschild radius. So if I squeezed it down, and for something like the sun, the Schwarzschild radius is around a mile. It's very, very small. But what if I were to compress the sun to be smaller than a mile? What would happen? Well, we didn't know. And to this day, nobody knows. What we know, we don't know what happens to that matter. But we do know that that special radius, the Schwarzschild radius, becomes something else. When you compress matter down below the Schwarzschild radius, you get what we now call a black hole. And that Schwarzschild radius gets a new name,
the event horizon.
Yeah. Exactly. So it was this tiny corner of general relativity discovered in the trenches of World War I, where Schwarzschild accidentally discovered black holes.
Okay, so he discovered...
That's a great origin story.
Yeah. I mean, unbelievable, in the trenches. But when did that become the theory of black holes themselves?
It emerged over the course of the 1940s and 1950s. So Schwarzschild is in the 19s, 1917, 1918, the height of World War I. It wasn't until the 40s and 50s that people really started to put these pieces together. And there were two threads that were happening that had to converge. One was the theoretical side, just poking and playing with relativity It's like you get a new toy for Christmas and you start, seeing how it can bend. You start seeing what it can do. Over time, physicists were just playing with this machinery, playing with Schwarzschild's equations, seeing what happens, seeing if they could understand the nature of that special radius, what happens to matter on the inside and the outside, what happens to space and time on the inside and outside. And then on the other side were observations, astronomical observations. Because at the time of Schwarzschild, there were stars and planets and asteroids and comets. That was it. That was our list of astronomical objects. It was a very short list. And none of these objects had their material compressed down beneath that special radius. So there was like, okay, great. Einstein's theory predicts that something weird happens at the distance, but nature isn't going to actually produce objects like that. And then we discover white dwarfs, which are very compact objects. These are the leftover cores of stars like our sun. And then we discover neutron stars, which are even denser, which a typical neutron star, you can take a small teaspoon of neutron star material and it outweighs like the Great Pyramids. These are extreme objects. And so we start to find in nature smaller and denser objects. And you look at a neutron star is right around the Schwarzschild radius. It's like the smallest object you can possibly have that's still larger than its own Schwarzschild radius. And so we started to ask, like, okay, what if you poked at a neutron star? What if you just made it a tiny bit smaller? Well, the math says that if you were to make a neutron star just a tiny bit more dense, just put it a little bit over a certain critical threshold, then its own gravity would be so strong that no other force of nature would be able to compete against it. And it would just collapse, not just below its own Schwarzschild radius, but the gravity would pull it down and to make it infinitely small, something we call the singularity. That's weird.
Yep.
People started to propose this, like, hey, maybe let's start looking for neutron stars that are just a little bit smaller, a little bit more dense. Maybe we're gonna make these black holes. And this is where the term started to get coined. I think it was in the 1940s, 1950s. We started calling these theoretical objects black holes. The community was split for decades. Some saying, you know what, there's nothing stopping nature from making a black hole, so maybe they're out there. And then other very reasonably saying, well, okay, yes, we just haven't figured out how nature is going to prevent the formation of black holes. Like, yes, according to our latest theory of physics, if you compress a neutron star, it turns into a black hole, but there'll be some other force, some other interaction that we haven't figured out yet that will prevent the formation of a black hole, which is a reasonable statement to make. Then we discover X-ray astronomy, where we are able to build telescopes that show us the X-ray sky. And we find one particular object, Cygnus X1, the brightest X-ray object in the constellation Cygnus, that's pouring out enormous amounts of X-rays. Like, it is incredibly bright. It is, I can't even describe how much brighter it is compared to your dentist's X-ray machine. It is just spewing out X-rays. We see this object and we're able to measure, okay, we've got this bright source of X-rays. This is obviously coming from a ball of hot gas, because hot gas has a lot of energy, it can emit a lot of X-rays. So, okay, it's this ball of hot gas is obviously orbiting around something. There's something at the center, but we can't figure out what's at the center. But we can use the temperature of this gas, its luminosity, its width, and all that to figure out the size and mass of that central object. We do the math, and then that central object is smaller than it's has a shorter radius, smaller diameter than a neutron star, and more massive than a neutron star. So all the observers are like, okay, so theorists, we've got this object that's denser than a neutron star, more massive than any known neutron star. What do you got on the menu? And the theorists are like, black holes? That's the only thing we got. That's our only explanation for the existence of this object. And they're like, okay, black holes it is. Nature makes black holes. Now we have mountains of evidence, including direct pictures of the existence of black holes. But that story, it took 40 years for black holes to be confirmed.
But they are really weird in themselves.
Of
the
course.
idea, like, there's these, because, again, if you think of as a kid, you think of space, things fly through space,
Yeah.
but you don't think you get to a point where it's like a hole in space.
It is.
And everything falls into it, can't get out, and what happens there?
Exactly. And, if Interstellar teaches us, it's a giant library, it turns out.
Yeah.
Black holes are weird. They're weird in many, many respects. One is their centers, which we call a singularity. It is a point of infinite density that all the material that makes up a black hole, all the material that flows into a black hole gets compressed down to an infinitely tiny point. We know that's wrong. We know that's an incorrect answer.
Because
there aren't actual places in the universe that have infinite density. That doesn't work. What the singularity is telling us is that general relativity is coming up short. Because when you try to work through the mathematics of general relativity, say, hey, Einstein machine, tell me what happens at the center of the black hole. The Einstein machine just goes, crazy.
Yeah.
It just infinities pop up and the mathematics becomes impossible to solve. So we're like, okay, that's not a proper physical theory. Physical theories are usually able to give you answers, give you some sort of response, but general relativity does not. It does not tell us what happens at the center of a black hole. So one way of saying that, instead of saying, okay, it's a point of infinite density, it's a point of infinite questions at the center of a black hole. We literally don't know. We need a better theory of gravity to explain what happens at the center of a black hole.
So I read something that said the math says there should at the center of a black hole should lead to a white hole.
White holes.
Yeah.
Okay, you're going there.
I'm excited by white holes.
You are excited. What excites you about white holes?
The idea that potentially that leads to other universes within black holes, but it's something we'll never be able to prove unless we go into a black hole.
Yeah, so one way to directly test our most advanced theories of what a theory of gravity beyond Einstein would be to venture into a black hole. And you would certainly learn something in the brief moments that you would survive, but you would not be able to communicate that out. And so to explain white holes, I need to explain the other side of black holes, or their other facet, which is that short shield radius, that event horizon, that one-way boundary. The gravity surrounding the singularity is so strong that at that distance, at that special radius, that special distance, nothing can escape. There's no physical boundary. There's no atmosphere. There's no layer. There's no flashing lights at the event horizon. It is simply the region where you get a little bit too close to that singularity, where that singularity's gravity is so strong that if you tried to turn around and leave, you can't. So black holes are one-way streets, and this is why we call them event horizons. They are places that separate one region of the universe from another. Once you're inside an event horizon, you can look out and you can see the rest of the universe because light from the rest of the universe is following you in. So you can look out, you can see stars, you can see galaxies. Someone waves to you from the outside, you can see them waving. But if you wave back, they can't see you. Because the light that you emit, the light coming off of your body, gravity is so strong, is pulling so hard that not even light can make it out the other side. So black holes are one-way streets in. It is possible to take the mathematics that describe a black hole, one way in, singularity, infinite, etc., and just reverse them. Just flip the signs on everything. The mathematics lets you do that. You just put a minus sign where you need it instead of going in and things are coming out. This is how we get the idea of a white hole. A white hole looks like a black hole, except it doesn't look like a black hole. That was a horrible way to start that sentence. A white hole still has a singularity at its center. It still has an event horizon. But the event horizon works in the opposite direction, where if you are approaching a white hole, you cannot enter it. So a black hole you can't leave, a white hole you can't enter. If you happen to be inside the white hole at the moment of its formation, if you're inside that event horizon, you will be driven away from the singularity faster than the speed of light, which means you can't turn around and try to re-enter. You're just flowing away from it permanently. There's no way to reverse that. I hate breaking people's hearts.
You're gonna break
and you've been so generous for hosting me here. I'm going to break your hearts. But I feel like it's important to create a safe space where we can be honest with each other.
I know what's coming.
I'm not going to say that it's impossible for white holes to exist. It's strongly unlikely that white holes exist. For one, and we can tackle this in two directions. Just like how we developed black holes from two directions, from a theory and an observation side. We're looking at the corners of general relativity. We're finding the viability of these objects within the theory. And then we actually saw them in the universe and we were able to make a match. White holes have trouble existing from both directions. One, we see absolutely no evidence of any white holes anywhere in the universe. And we've looked really hard and we found really, really, really weird stuff. Not just black holes. We found fast radio bursts. We found quasars. We found hypernova. We've done our homework in astronomy. We're not done. There are always more surprises around the corner, which is why I don't want to close things off completely. But as of now, we have seen absolutely no evidence for any white dwarfs. Sorry, white holes. Yep. On the theory side, white holes have a lot of challenges existing. And that's because of the way they're constructed. Just because you can put a minus sign in front of the equations and reverse everything doesn't mean you have a physically viable object. For example, I can describe a waterfall with the droplets of water falling down from gravity. I can model that. I can use things like the Navier-Stokes equations to model the fluid flow over the crest and like down the hill and incorporating gravity and all that. I can do that. I can put a minus sign in front of those equations. I can describe mathematically a waterfall that starts at the bottom, climbs up, and goes over the top. And you know what? The weird thing about physics, there's nothing in principle stopping that reverse waterfall from existing. Except that's not how waterfalls work. There are other forces of nature. If I just tackle it with gravity, with my understanding of gravity, I can have a reverse waterfall. But then once I incorporate other theories of physics, like say entropy, the flow of heat, all that, then I can see, okay, reverse waterfalls. I should not expect to see a reverse waterfall in our universe. I can construct a white hole in the theory of relativity if I just look at the force of gravity in isolation. But gravity's not the only game in town. There are other theories of physics, other aspects of our universe that get to have a say, things like entropy, and those things say, no, you can't have a region of space that is just spewing out matter all the time. That is not, you should not expect to see something like that in the physical universe.
Okay. So in terms of black holes, if we know the singularity is unlikely, the physics,
or we just don't know.
We just don't know. Where are scientists putting their attention on black holes? What is it they're trying to figure out?
Ironically, scientists right now, over the past, say, 10 or 20 years, and if you thought the past hour of our conversation was weird, it's about to get much weirder, is not in the singularity.
Okay.
That's not where we're focusing most of our attention right now. It's at the event horizon.
Okay.
Because the event horizon in many ways is even weirder than the singularity, because the singularity is just a mystery. Like, what happens at the center of a black hole? I don't know. Okay, that's it. There's going to be something. Like, if we had a better theory of gravity, we would be able to describe what happens at that center. But we don't, so whatever.
Could it just be a big ball of stuff squashed together?
Possibly, yes. Yeah. That seems unlikely. Or like the theories of physics beyond gravity, the theories of gravity beyond general relativity, some of them do say there's just like a little hyperdense nugget of matter. But those theories aren't exactly working out in other respects. So, who knows? The event horizon is super weird. The event horizon, the presence of a one-way boundary in the universe opens up a lot of issues. And the central issue is what the heck goes on with information.
Oh, this was Stephen Hawking.
Oh, yeah.
Yeah.
Yeah, here we go.
Yeah, it just like erases information. I think I heard Brian Cox talking about this on Rogan.
Yeah.
He's talking about it erases information.
Or it might, or it might not. Yeah. We actually don't know. So, like, prior to Stephen Hawking, you've got this one-way boundary in the universe. And we're just going to assume that information is preserved in our universe. Like, just like you can't create or destroy energy, you can't create or destroy information. Like, there's a bunch of information that describes this room, the positions of all the atoms, their momenta, their spin states, their electricity. You can make a long list of all the things that describe this room. If you chuck it in a black hole, if you chuck it in a black hole, that information isn't destroyed. It's just locked behind the event horizon. We can't access it, but it's still there. Nothing's destroyed. Everything, that's fine. Whatever. I have money in a safe deposit box, and if I lose the key, the money isn't destroyed. I just can't access it. But that's fine. There's no violation of physics right there. Then Hawking came around. And in 1976, Stephen Hawking discovered that black holes are not entirely black. We've been using the wrong name this whole time. He discovered that there is this very subtle interaction between the event horizon and the quantum fields that make up matter. And this very subtle interaction leads to the emission of radiation. That particles and radiation naturally, spontaneously come off of the surface of a black hole. And I know I just said they're one-way boundaries, they're completely black. It turns out that's only in relativity. That's only from a picture of general relativity. General relativity is not the only game in town. Mm-hmm. There's also quantum mechanics. And quantum mechanics gets to...
The really weird shit.
Yeah, it gets to come in here and say, hey, I think there's something... You got just a little change here. So black holes are not entirely black. They do emit a little bit of radiation. It's not much. For a typical black hole that's a few times the mass of the sun, we're talking like 1 photon a year. These are not exactly hot objects, but they do emit radiation. And as they emit radiation, they lose mass. And eventually, given enough time, 10 to 100 years or something like that, they go away. They disappear. Poof.
Black holes disappear.
Black holes disappear. Black holes are not permanent objects. This is Hawking's discovery.
Huh.
Yeah.
Where the hell do they go and where's everything in it?
I mean, this is the key. This is it, because
what?
They just evaporate. Black holes evaporate.
I never knew this.
This is Hawking's radiation. The radiation emitted by the black hole, someone has to pay the piper. The mass and energy for that has to come from somewhere. It comes from the black hole itself. They emit radiation. And then they eventually disappear. It takes an incredibly long time, much longer than the present age of the universe, but in principle it happens, and that's important because now we have a mechanism for destroying black holes. The problem and how information works into this problem is that Hawking radiation by itself does not contain any information. It's a special kind of radiation that we call thermal radiation. It's the same kind of radiation that just warm objects emit. this radiation is random. It doesn't contain information. It doesn't contain anything. There's nothing useful you can learn. So now we have a problem.
Yeah.
And the problem is we have discovered a mechanism to destroy information in the universe, because we can put information inside the black hole, then it radiates, and that radiation carries no information with it, and then the black hole goes away. Where'd the information go? I have broken something. This is called the black hole information paradox, because we're getting something wrong. This is why we're so excited by event horizons, more so than singularities, because paradoxes are very interesting and exciting, because they are telling us that we are getting something wrong. And it's just a clear sign, like, you are getting something wrong about the universe when it comes to your understanding of black holes.
Are there any theories?
Go do homework. Of course there are theories. Well, we've got loads of theories.
What's your favorite theory? Or that you think, not favorite, like, because that could be the most fun one, but is it the one you think's most likely, or do you have one?
There aren't any good ones. Okay. Honestly. So I'll get to say it again. I don't know. There are fun ones and interesting ones. There aren't really any good ones.
Okay.
There are some lines of thought that say, let's just go crazy. That black hole surfaces are actually series of interconnected wormholes, which that sounds pretty cool. There are other ideas out there that say, black holes are not three-dimensional objects. They're actually only two-dimensional objects, that only their surfaces matter. And in fact, that informs us about our entire universe. This is called the holographic principle, where our universe is actually only two-dimensional, and what we perceive as three dimensions is an illusion. Those are the two main contenders. Is the I would call it the holographic principle, and then this like fuzzball idea are the two main contenders for attempting to solve this.
If it's a wormhole, does that not mean everything that's going into the black hole is being spat out somewhere else in the universe?
It's more of not just a single wormhole, but a bunch of tiny microscopic wormholes, where everything that falls into the black hole ends up being correlated or connected to the space-time structure outside of the black hole in a way that we don't fully understand.
Okay.
And then when the black hole dies and goes away, it still leaves this imprint in space-time around it that is able to preserve the information. So almost like there's a duplicate of the information when it enters the black hole, or there is a quantum connection there.
Okay.
Yeah, this is getting intense.
It's very important that you don't lose this, okay? This is your inheritance through Bitcoin.
Let Bitcoin rip. Don't rip up your Bitcoin. Set up inheritance with Casa.
So does this take us to the point where we have to then talk about quantum?
Yeah.
Okay.
Right here.
Okay. Even Einstein thought it was weird.
Are we still on your first page of questions?
Yeah,
okay.
But sometimes I never even need the questions. Sometimes I never even use them, because there's loads just in case. So quantum is also something that Einstein thought was weird.
Oh, yeah, which is ironic because Einstein was one of the pioneers of quantum theory.
And quantum theory and relativity can't align.
Quantum theory and special relativity totally align. We figured this out, and we called that unified theory quantum field theory, which is very cool and very special and a lot of fun. But quantum mechanics and general relativity do not get along at all. And this is one of the first things we recognized as soon as we developed both things. Both relativity and quantum mechanics were emerging in the same time frame in the early 20th century. And they're two very powerful theories, very useful theories. As far as we can tell, both are individually correct, but we can't get them to talk to each other.
Do you want to do the basics of quantum mechanics for anyone listening to understand? I understand it's the theory of that very small.
That's it.
Micro level.
Just like relativity, we started to encounter relativity once we started to attempt to understand things that were traveling very quickly or had an incredible amount of mass. Quantum mechanics emerged as we were trying to understand the very small. And it turns out, because nature isn't simple, that very tiny things, subatomic things, do not play this by the same rules, as the macroscopic world. And things that we assume to be true about how the universe works simply break down at the subatomic level. Just like things we assume about the nature of space and time break down once we encounter very massive objects or very, very fast-moving objects, they simply break down. It's just there's a different set of rules there. There are a different set of rules that apply to the subatomic realm. These rules are encapsulated in a series of mathematical statements that have emerged and unified to become our quantum theory of physics. Unlike relativity, we have no straightforward explanation for how these rules emerge or how to picture these rules, because the rules are very, very weird. Rules like objects can exist in multiple places at once, and that's no problem. Objects can spontaneously appear on the other side of boundaries the next time we go looking for them, with no movement, no motion whatsoever, and that's no problem. There are rules like probabilities are everything, that you can't precisely determine the motion, the momentum, or position of a subatomic particle. You can only assign probabilities to where you might see it the next time you go looking for it. Where there's this whole thing where matter isn't really matter, it's also kind of sort of made of waves, and the waves are waves of probability that interfere with each other in complicated ways. These are a bunch of bizarre, absolutely bizarre statements about the world that work because they give us a theory of physics, they allow us to make predictions, verified by experiments. Quantum field theory is perhaps the most well-tested theory in all of physics, in all of science. And yet, we can't explain how any of this works. And that was one of Einstein's big objections to it. And it also, quantum theory says really weird stuff about the universe beyond what I just said that Einstein was repulsed by.
Such as?
His biggest thing was this effect called superposition. Superposition was initially identified by Erwin Schrödinger, one of the giant founders of quantum mechanics. Schrödinger himself would end up hating quantum mechanics and turning away from it in disgust, even though he himself was one of the pioneers. The Schrödinger equation is one of our fundamental equations of quantum mechanics. Superposition tells us that if I take, say, two particles, and I bring them close together, I get them to kiss a little bit, they become entangled, where I can no longer describe a single particle in isolation anymore, which is weird, because normally when I think of, say, two particles, I've got particle over here, particle A and particle B, and I write down the properties of particle A, and I write down the properties of particle B. Like you and me. Let's switch metaphors here. Like I've got my life, and you've got your life. Right now, we are in this room, and we are briefly our lives are intersecting, and so we describe the interactions between us, the conversations between us. But then I'm going to get on a plane and go back home, and from then on, until I share this episode and you share this episode, but I've got my life and you've got yours, completely and totally separate. That before our interaction and after our interaction, we've just got our own lives, and I don't need to care about you to figure out the future trajectory of my life, and vice versa. Quantum mechanics is different. At the subatomic level, if we were electrons instead of human beings, I've got electron A over here, electron B over here. I've got all my physics, and I can predict the motion of electron A and electron B. And then they come together. They have a brief interaction. Maybe they bounce off of each other. And then they leave. No longer can I describe these electrons in isolation. They're connected together at a very deep, very quantum level. They become entangled or correlated, where what electron A does in its future influences electron B. It's like if you and me, after this conversation, years from now, something happens in your life and it affects me with no communication. You didn't pick up the phone. You didn't call me. You didn't text me. I didn't watch, see you on my social media feed. I had no clue. There was no exchange of information whatsoever. But something in your life happened and it directly affected me. And it sounds like I'm talking about the paranormal. It really does. It sounds like I'm talking about ghosts and stuff. I'm talking about subatomic physics. And it's very, very, very real. Einstein took one look at that. Schrodinger himself took one look at it and said, 9, no, I can't do this. Because you're talking about non-local physics. You're talking about an atom in the Andromeda galaxy affecting the outcome of an experiment here on Earth. How is that supposed to work? Tell me. This was Einstein's challenge to the rest of the physics community. People like Heisenberg and Bohr, some of the other developers of quantum theory. He would look at them and say, how is this supposed to work? How am I supposed to believe the results of any experiment? Because you're telling me that any experiment I can do can be influenced by the motion or identity or behavior of any particle throughout the universe because we're all entangled, we're all correlated together. No one had an answer for Einstein.
But it was provable. You could scientifically prove these.
That's the thing. After Einstein's death, and so or during the time, let me back up a little bit. During the time of Einstein, during these great debates between like Einstein and Schrodinger on one side, who are challenging the physics community to come up with a picture. And like, seriously, you want to abandon locality in physics? Like, that's kind of important that when I build an experiment here, I can control all the variables and I can predict the outcome. And I know it's because of what I changed. Like, that's central to science. But you're telling me locality is something that we can just toss out the window when we feel like it? The general response of the physics community was, shut up, Einstein. You're old. You're getting senile. Schrodinger, you're a weirdo anyway. Thank you for your equation, but, was just shut up and calculate. Because as nonsensical as quantum theory was coming out to be, it was still correct. It was still able to make predictions. And we would verify those predictions against experiment. And then after Einstein's death, we tested this. We were able to come up with some very, very clever tests called the Bell inequalities of this concept of entanglement. And it works. These particles, when they come together and then they're separated, and it could be electrons, photons, whatever, are entangled. They are correlated. Physics is non-local. We're able to verify this experimentally. How this works and what this means for the macroscopic world, we have no idea, even more than a half a century later. We have absolutely no clue what this is supposed to mean. Does it all just go away at macroscopic scales? Is there something else that we're missing? How does the universe work this way? How do these electrons, these subatomic particles, how are they correlated? How is this supposed to work while not violating locality and all this? We don't know. We don't know.
But it's weird. What is it? So the implications for it are...
Of what?
Quantum entanglement. The fact that we've got these things, like, why would Schrodinger and Einstein want to run away from it? What were the implications for them?
They hated several things about quantum mechanics. Einstein's big objection was the loss of locality.
Yeah.
It's like, come on, really? We have spent millennia crafting theories of the universe that are local. Local causes have local effects. If I'm nearby you, I can influence you. If I'm far away from you, I can't influence you anymore. This is not just physics, but like rationality. Like, why should the Andromeda galaxy affect how I live my life? Why should a little hydrogen atom in a star 10 billion light years away affect the outcome of my experiment? And it doesn't. We see no evidence of those kinds of connections. So why does quantum theory appear to be non-local? What is going on? We don't know. That was his big objection. Schrodinger's big objection was that it came down to the nature of this wave-particle duality, this aspect of reality, of subatomic physics, where we can't describe individual particles as a single particle, as a single defined object like a tiny little bullet moving through the universe. Instead, we have to describe it as a wave, where this wave is propagating itself throughout the universe. And the wave tells us where the wave is more dense or where it's peaking. That's where we expect to find the particle the next time we go looking for it. And then where the wave is less dense or the wave is more spread out, the trough of the wave, that's where we shouldn't expect to find particles. And the problem, Schrodinger's problem with this picture, which is an unresolved problem, is that it seems like we have two sets of physics here with quantum mechanics. That there's one set of physics that when nobody's looking, everyone turn around, we get a bunch of waves. And we have the Schrodinger equation for describing the evolution of these waves. They propagate themselves through time, just like normal waves would. And then we go look, and all of a sudden, the universe knows to turn off the waves and just give us particles. We never observe a wave. We only observe the actual particle interacting with our detector or our eyeballs.
Weird.
It is weird. And Schrodinger's like, come on, people. Are you serious that the universe knows when we're not looking to be a bunch of waves? And then we turn around and then all of a sudden it's a bunch of particles. And then we have, when no one's looking, we have this slow and steady evolution of the waves, and we have, normal mathematics to describe it. And then all of a sudden we take a measurement and a switch just goes off. And we even give a name for this. We call it the collapse of the wave function. And we're just supposed to accept that as being fine.
Is this where we have to get more philosophical?
I mean, science is philosophy.
So somebody gave me an analogy for this. They said, when you're playing Grand Theft Auto,
as Schrodinger was, he was huge.
Yeah, the whole universe or the world of Grand Theft Auto isn't built. If you drive from one end of the city to the other, when you get to the other end, there's cars there and people there on the street, but they only exist once you come into view. And somebody said, this is similar. This is similar. This is why the simulation theory has some kind of a reason to debate it.
Simulation theory we can get into.
Yep.
That is a fun discussion. I don't think that a basis for the simulation theory will come from quantum mechanics, because it's not that the universe doesn't exist until it comes into view. It's that we have one set of physics to describe how it exists when there are no measurements being taken. That's all the wave function stuff. And then the moment we go to make an observation or a measurement, it snaps to be a different set of physics. And there's a little subtlety there. It's like we're changing one kind of physics for another at the moment of observation or the moment of measurement.
Because we don't have a unified theory. No?
It's the fundamental problem with this is that we don't understand quantum mechanics.
Okay.
We don't understand this beast that we have created. We are able to predict the results of experiments, but like I said, we can't put into words how this is supposed to work. And that was Schrodinger's big objection. He said, please, would someone just explain to me how this is supposed to work?
Are we getting a better understanding? Is there work being done or is it just too fucking weird?
There's yes and yes. There's work being done, and it's weird. We have the sense philosophically that we're missing something with quantum mechanics. And this was Einstein. He went to his grave believing this, that something is off with our understanding of the subatomic world. Considering that we only uncovered the subatomic world 100 years ago, this is very recent in terms of human understanding. I don't think that quantum mechanics will be replaced in that sense, but I do believe that hopefully centuries from now, we'll have a more complete understanding where things do make sense and hook into each other in sensible ways.
Okay, fair. Okay, whilst we're here, let's do simulation theory.
Okay,
I
sure.
think, so I'm intrigued, but I don't think we're in a simulation personally, but you never know. Elon Musk, I think, said he thinks there's like a 1 in a billion chance we're not in a simulation. I think Neil deGrasse Tyson even said it's 50-50 chance. What are your thoughts on the theory itself?
So it's a fun thought experiment.
Yeah.
And the thought experiment comes to us from Nick Bostrom, a philosopher.
Yes.
Oxford
MIT guy. Is he?
Oxford,
Oh, is he?
actually.
I thought he was MIT.
Maybe his, dual appointment.
Yeah, maybe.
Either way, wherever he is, maybe in one of the universes he's at MIT. It's a very fascinating argument. It is an original argument, but like all topics in philosophy and even science, it doesn't stand in isolation. It comes from a tradition of thinking. And this tradition of thinking in philosophy is realism. It is like, does the universe exist independently of our minds? Awkward pregnant pause here. We don't know. Philosophically, there are different approaches to this. Like maybe we manifest reality in our minds. Maybe reality does exist independently of us. Maybe reality exists independently of us, but it becomes modified on its way to being consciously aware of it. There are a lot of fun, like beautiful, powerful philosophical questions here that end up informing a lot of science. Like science itself assumes that reality exists independently of our minds. That is a foundational assumption of physics, that everyone agrees that there's an electron there and that it has an independent existence from our own awareness or observation of it. Anyway, that's a whole other discussion. So Bostrom's argument comes from this line, and he makes an observation in his paper where he outlined this, which is, computers get more powerful with every passing day. We are able to create ever more faithful representations of the universe every single day. And that, we can, I'm a cosmologist, I'm a computational cosmologist. I build simulations of the universe where, galaxies emerge and light propagates from here and there, and even stars pop up. And you can imagine advancing this far into the future, that in principle, someday we could build a super duper computer, like a computer the size of a planet or something, that could faithfully recreate all the physics of the universe. And I mean all of it, not just galaxies moving around, not just star formation, not just planets emerging. I'm talking water molecules interacting. I'm talking sodium ions moving around, where I could faithfully resimulate every aspect of the physical universe in this planet-sized supercomputer. And that following all the laws of physics, in this simulation, you would have simulated life emerging, all the calculations being done behind the scenes to tell which electron to move over here and this atom to interact with that ion over there and do all the things. And eventually you would lead to consciousness. And then what you would have are conscious beings inside this computer who look around and they see photons entering their eyes. They have sound waves propagating. We're out here doing all the calculations. But then inside the simulation, it just looks like the universe. And it would be described by fundamental laws that we would try to understand. We would create telescopes to observe the different distant corners of the universe. And in principle, it might be possible to build such a universe that is so faithful to the OG universe that we don't know, that we never discover that we're inside of a simulation. So that is Bostrom's main argument. From there, he leads to what he calls a trilemma. There were three possibilities come out of this. One possibility is that, it's almost guaranteed that we live in a simulation, because if you can do it once, It's just a numbers argument that, if I could build a supercomputer that can simulate the universe and it takes like one planet to do that, I turn one planet into a supercomputer, I can do this a whole bunch of times. And a sufficiently advanced alien civilization could do it a whole bunch of times. And once you do it enough, then the number of conscious beings that live inside of a supercomputer vastly outnumber the number of conscious beings that don't. Like the number of Minecraft creatures or Grand Theft Auto characters vastly outnumbers the 7 billion or so human beings on the planet. And so just by raw numbers, we're probably in a simulation, because if you just ask what are the raw probabilities of my conscious mind being simulated, it's very high. Like 99% of all conscious beings are simulated. That's one potential option. Another potential option is that we can't. That it turns out you can't build a faithful recreation of the universe. Or that when you do, the beings inside of it are able to discern that they live inside of a simulation or not. They are able to demonstrate it. And that for some reason, building a faithful simulation of the universe is impossible. The last trilemma, and I think I'm remembering this right. My apologies to Professor Bostrom if I'm misremembering that. Is that any advanced civilization that becomes capable of building simulations ends up killing themselves? Yeah, like some sort of great filter. And so we don't live inside of a simulation, but also this is the end of the line. That's a trilemma.
Yeah,
3 possibilities. Now, what you can try to do is introduce extra arguments or nuances into this to try to break the trilemma, to make one of these more possible than the other. Any attempts to assign probabilities to this are nonsense. Just pure speculation, which I shouldn't say nonsense. It's just speculation, but you cannot say it with any authority. If you say it's 50-50, you got to back those numbers up, Dr. Tyson, and you can't. If you say it's 1 in a million, back those numbers up. Come on, Elon. Don't you have other things to do? Apparently not. I don't know. You got to back those up. It is a genuine trilemma, or at least the argument presented in Bostrom's paper is a genuine trilemma. And so that's where we are. There are ways to discuss each of these 3 options and assess which ones are more likely than the others. But at the end of the day, it's with our present state of knowledge.
We don't know.
We don't know.
We don't know. That's going to take me to a guaranteed next we don't know. The thing I think about most that really weirds me out is the beginning of the universe.
Oh, yeah.
And you probably discussed this a million times to the point of boredom. I think about this a lot. And I go around in circles with it, probably as everybody does.
Yes.
Because I'm like, our best estimate is what? The observable universe is 13.8 million?
13.77 billion years old. We're really proud of that second decimal point.
I rounded up. But by the way, on that we say the observable universe. So could it be just much bigger?
Oh, if it almost certainly is much larger than what we can observe.
So 13.77 is just the arbitrary measure that we can use because we can't see further back.
It's not the arbitrary measure. It is not an arbitrary measure. In fact, this is one of those numbers that all observers can calculate. Anyone in the universe, even outside of our observable horizon, can calculate this number. And they can all arrive. They wouldn't use years, obviously, because they don't live on an Earth orbiting the sun.
Yeah.
But once we do the appropriate unit conversion, we can all arrive at this same conclusion. And that is the whole entire universe, not just our observable portion.
Started.
The whole observable universe 13.77 billion years ago was a singularity.
Okay. So,
which we know is wrong. Hence, and many of the mysteries.
Yeah. Okay. So the observable universe is a lot bigger, but the starting point was 13.77.
Exactly. We all agree on the starting point.
We agree on that. So, why then? You don't know.
Well, the universe is the evolution of the universe We are able to tackle this through general relativity. It turns out it's another exact solution, one of the 17 known exact solutions to general relativity. These are called the Friedmann equations, named after Alexander Friedmann. There were several other people working on this at the time. There was a Belgian priest, Georges Lemaitre, who proposed a primeval atom that gave birth to the universe. Everyone laughed at him and said that is way too Catholic. Come on. Turns out he was right. And then there was Robertson and Walker, two American physicists. And so another solution for this, or another name for this, is the FRLW metric. Friedmann, Robertson, Lemaitre. Who'd I forget? One of them. Walker.
You would know, not me. You didn't say Walker twice.
I did. Did I say Walker? Anyways, those four dudes. Those four dudes did it. And what this tells us, what this solution to relativity tells us, is that the evolution of the universe, how quickly it expands as a function of time, is intimately tied to its contents, to what the universe is made of. So if you fill up the universe with different kinds of things, if you fill it up with radiation, if you fill it up with matter, if you fill it up with pure energy, and you have different proportions of these various kinds of elements, you get different histories of the cosmos. So the universe is 13.77 billion years old because of its proportion of components, which is roughly 4 to 5% normal matter, the matter of you and me. Atoms, protons, neutrons, things like that make up an incredibly tiny fraction of the universe. Another 20, 25% or so is made of dark matter, a form of matter that is currently unknown and mysterious. It's invisible, but it has gravity, which is how we know it's there. And then the remainder is pure energy, something we call dark energy. We do not understand dark matter and dark energy at all, but we can measure their properties. And based on the measurement of those properties, it's something, all right? Give us something here in cosmology. Based on that, we can put these into the Friedmann equations and we can calculate an age. So that's why the universe is the way it has that age, because this is what it's made of. And then your next question is, why is it made of this? And, we don't know.
Yeah, it's the whole, all this can come from nothing.
I don't even know. We don't even know if that's the right statement.
Yeah.
I think a better phrasing of that question, which is an old philosophical question and religious question and scientific question, which is, why is there something rather than nothing?
Yeah.
And we don't know.
We don't know.
We've never known.
And every answer to that question is, well, what came before that? And exactly. Why? And the other one I think about is that we have this universe in wherever we are here, this universe we're in, that appeared out of nothing.
We don't know.
We don't know. But do you know what I mean? It came to appear. Could there be other universes that have come to appear in other? And I'm not even thinking multiverse here. I'm just thinking, when a universe appears,
what else happens?
Yeah, what else happens?
We don't know.
Yeah.
I mean, you did just literally describe the multiverse.
I know. But I don't think of this connected multiverse. I just independent universe.
Yes. This isn't the Marvel multiverse, unfortunately. No multiverses are connected together. No matter what. No matter how you approach this, no matter how you construct a multiverse theory, we're all separate entities. Yeah. I told you I'm here to break hearts.
I know,
but it's
the most. I mean, I find it all so fascinating. I have these moments. I'm like, why are we here? What are we doing?
Why is there something rather than nothing? That's why I never.
I'm glad there's something rather than nothing.
I mean, I prefer it.
Yeah.
Yeah.
If I had to choose.
I like this universe. It's pretty fun. I keep my own personal religious views close to my chest. So do most scientists, actually. and they do not see a conflict between what they work on and what they believe. But I do not begrudge people for saying, well, the universe was created by God. And then you say, well, why does God exist, or the gods exist? And they say, well, they've always existed. There's just an intrinsic property of godness. I don't begrudge people for ever saying something like that, because it's not like we have any better answers.
No. What do you, what are the things that you think about as a spaceman, as an astrophysicist, as a scientist? What are the things that you think about most, that you wrestle with? You're like, this blows my mind.
Oh, there are many things that keep me up late at night, and have always drawn me to this field of astrophysics, of cosmology, of the study of the wider universe. And it is rejoicing in that I don't know. Like, we don't have good ideas about the origins, quote unquote, of the universe. There's some interesting speculations. Some are motivated by string theory, others motivated by theories of advanced quantum gravity, that next step in gravity, the same kinds of solutions that we're trying to tackle the centers of black holes, we are also trying to use to tackle the extremely early universe.
What is string theory? I've heard Eric Weinstein talk about it, and I've just gone, I have no idea what you just said then.
String theory is an attempt to unify quantum mechanics with relativity. It is an attempt to bring these two theories in accordance with each other. To make that happen, to make that link happen, string theory radically re-envisions the physical universe and what it's made of. Just like relativity radically reimagined how we approach space and time, just like quantum mechanics radically re-envisioned how we approach subatomic particles. Now we need to think about waves and entanglement and all that. String theory radically rewrites what the universe looks like. And according to string theory, what we call subatomic particles are nothing but they're really tiny bits of strings, of bits of energy that are vibrating. And just like different guitar strings can be plucked and they give off different notes, these tiny strings of energy can have different fundamental vibrations in them. The different vibrations manifest themselves as the different varieties of particles. So a string vibrates this way, it's an electron. It vibrates that way, it's the photon, and so on and so on. What made string theory very intriguing and promising, especially early on, it started out actually just as a theory of the strong nuclear force, as an attempt to explain the strong nuclear force, and kind of sort of did it. And then we developed other ideas involving quarks and gluons, and those became enormously successful. But we found that one of the ways we could pluck one of these strings would lead to the force of gravity. And so that's why string theory all of a sudden became so fascinating, because here we had a theory of particles, a subatomic theory, a theory born from quantum mechanics that was naturally giving rise to the gravitational force. That was the first time, and as far as I know, the only time that we've been able to make a connection from quantum physics to gravity. String theory also says some very strange things about our universe beyond just that particles are really tiny bits of vibrating energy, which is that our normal 3 dimensions of space are not enough, because the 3 dimensions of space aren't enough, don't give these strings enough freedom to vibrate in all the ways that they need to vibrate to produce all of the known particles. In order to reproduce all of the known particles, you need more spatial dimensions. You need 10 or 11 spatial dimensions. Most of these dimensions would be unobservable to us. We have our 3 dimensions that we don't see any extra spatial dimensions. We kind of would have noticed by now. We don't. So these extra spatial dimensions have to be really curled up. They have to be really compact. They have to be closed up on themselves to incredibly tiny scales. So much so that when you say move your hand around in the air, you are circumnavigating these tiny dimensions trillions of times with every millimeter of movement. You're constantly swimming around them and circling around them as you move throughout our 3 macroscopic dimensions. This is great. This is cool. This is mind-blowing. Also, string theory itself is on very, very shaky ground these days.
Okay.
For 2 reasons. The same 2 reasons as black holes, as relativity, white holes, and it's both through the theory side and the experiment side. On the experiment side, string theory predicts more particles than what we currently know of. So we have our electrons, we have our quarks, we have our neutrinos, we have all the known particles, of which there are a zoo, there are many of them. String theory predicts, predicts is a strong word, and I'll get to that when I talk to the theory side, about the theory side, but string theory says that there ought to be many, many other particles out there. We call these the supersymmetric partners of our particles. The Large Hadron Collider at CERN, at the Swiss-French border, was designed in part to go hunting for these extra particles, and they found nothing. They found nothing. So that whole branch of physics, of particle physics that had been developing for 30 years of searching for these certain kinds of extra new particles has turned up nothing. So far, things might change. They just finished some upgrades. So they might change in the next few years, but so far we've got nothing. To the point that many of those theories are actually ruled out. On the theory side, I use this word that string theory predicts. String theory actually doesn't predict anything. That's because we don't know how these extra dimensions curl up on themselves. There are a bunch of them. There are like 7, maybe 8, depending on the string theory, on the version. They curl up, and they can curl up in all sorts of weird shapes. It doesn't have to be simple. They can like loop around, they can twist up, they can fold up. There's something like 10 to the 52 possible ways that these extra dimensions can curl up on themselves. We don't know which one of those corresponds to our universe, and we don't know why it'd be that one and not the others. And this is the big and. Let's say there was only one way for these dimensions to curl up on, not 10 to the 52, but just one way. And we didn't have to worry about which one is our universe, which way the dimensions curl up. Let's say there was just one way for all these dimensions to curl up. We don't know how to generate the particles of our universe from that curling up. We know in a broad sense in string theory that different vibrations lead to the particles, but we don't know how that process actually happens. And not in a quantum mechanics stuff is weird sense, but in a mathematical sense. We can't go from step A to step B. Like, oh, cool, different vibrations lead to different kinds of particles. Well, how do the vibrations occur in a certain structure of space, and how does that lead to the variety of particles that then go on to a physical theory of how these particles interact that I can test and experiment? We don't know. String theory, despite decades of work, has not been able to crack that. They have not been able to build that bridge. String theory itself actually cannot produce predictions. Like if we had a super duper particle collider opening tomorrow that could explore the scales of string theory, that it could explore those extreme energies, those extremely tiny scales, we could not tell if string theory was correct or not, because string theory itself can't create predictions for us to test against. So on the theory side, there have been all these issues with string theory, known issues, unsolvable math problems, basically, that for decades, string theorists have been saying, no, we're going to get it any moment now. We're almost there. Trust me. I mean, I grew up in the 1990s. I was reading Brian Greene's book in high school, about string theory, Elegant Universe, one of the books that got me on the path to physics. And in that book, he's like, don't worry. Soon we're going to do it. Brian Greene's still at Columbia. He's still giving lectures. I've been to them. I've talked with him. We're not there yet. And so at a certain point, after a few decades of working on something, when you haven't made progress, maybe it's time to think of something else. And then there's the whole experimental issue where string theory doesn't necessarily predict, but it does expect a whole variety of new particles, and we don't see those particles. We have not seen them. And it's not just a matter of like looking hard enough, as they're supposed to appear at certain energy scales and they simply don't.
Okay.
So string theory itself is on,
done to me.
It's on thin ice. It's on thin ice.
Are there alternate theories?
There are, but and if you talk to the people behind those theories, they'll tell you that, they're any year now we're going to make progress. But they're just as sketchy as string theory. One of the main contenders is loop quantum gravity. Loop quantum gravity is a theory of gravity that basically says that space and time itself are quantized, that they come in tiny little chunks, that space and time are not smooth and uniform. Instead, it's essentially the universe is pixelized. That too has trouble making predictions and being internally consistent with itself and matching up to the universe. But don't worry, any year now, we got this. Just one more bit of funding, please. Just one more year, we got this.
One more bit of funding.
I mean, I'm not trying. I'm not trying to be too cynical about this, because there are many good-hearted people, well-intentioned people, and these are the best ideas we've got.
At Ledden, we built the best Bitcoin-backed loan platform in the world. Proven, trusted, growing. Ledden's proven track record speaks for itself. Visit ledden.io/Mr. Obnoxious to get started. Ledden, there is no second best. Ledden is not regulated in the United Kingdom. Any credit products or virtual asset services provided by Ledden are not subject to UK regulatory protections. Please consider the risks associated with virtual assets and consult a financial advisor before making any decisions.
Right. Going back, to dark energy and dark matter. We know they exist.
Yeah,
because we can measure them.
Yep. Because they have effects in our universe, and we measure those effects.
And there's no alternate theory that it could be something else.
Which do you want to start with, dark matter or dark energy?
Dark matter.
Dark matter. Okay, here we go. By now, basically, no. When we first encountered dark matter, was actually way back in the 1930s. An astronomer, Fritz Zwicky, Swiss-American astronomer, fantastic guy, noticed he was looking at clusters of galaxies, the largest gravitationally bound structures in the universe. These are home to like 1,000 galaxies at a time. And the galaxies are buzzing around inside of the galaxy cluster. And he was able to measure the speed of these galaxies. And he noticed that the galaxies are way too fast. For the speed that they were traveling at, the cluster should have dissolved billions of years ago. Immediately, he recognized there had to be an additional source of gravity. There was something that was keeping these galaxies bound to the cluster that he could not see. He called it dark matter. The name stuck. He put down the problem. The astronomical community, put down the problem for decades. And then in the 1970s, Vera Rubin was studying the motions of stars in other galaxies, Andromeda and a few other nearby galaxies. And she found basically the same thing. Stars are moving too quickly. If you add up all the visible matter in a galaxy, calculate the gravitational pull of all that matter, it's not enough to account for the speeds of these stars. Galaxies themselves should have dissolved billions of years ago based on these speeds. They should not be held together. There has to be an additional source of gravity. So right away, you've got two options. Option one is there's some other component to the universe that is not immediately obvious. There's some sort of matter that has gravity, and that gravity is holding on to everything. Or you need to change your theory of gravity. Maybe Newton was wrong. Maybe Einstein is wrong. We've been in both positions before, so this isn't exactly an uncomfortable place. That was the 1970s. That was like 50 years ago when Vera Rubin discovered this. In the meantime, we've come up with an enormous amount of observations, an enormous number of measurements and observations that confirm that this dark matter mystery exists. It's not just inside of galaxies. The problem isn't just there. It's not just inside of galaxy clusters. It's the evolution of the largest structures in the universe. It's the appearance of some of the earliest things in the universe, something we call the cosmic microwave background, this leftover light from when the universe was 380,000 years old. We can directly observe it. We can see that light. We can see that radiation. Anytime you come up with a theory of dark matter, you say, okay, I want to explain this whole set of mysteries. I can come up with a new ingredient in the universe, or I can come up with a new theory of physics. One of the earliest new theories of physics to explain this was called MOND, or Modified Newtonian Dynamics. When you, anytime you attempt a new theory of physics that goes beyond Einstein, you end up falling short. You cannot explain the wealth of observations we have with a new theory of gravity. You might be able to explain galaxies. Maybe you stretch things a little, and sometimes you can explain galaxy clusters. But then when you go to explain the appearance of large structures, gravitational lensing measurements, the cosmic microwave background, heck, even Big Bang nuclear, on and on and on and on and on, you get the wrong answer. Every single time, any attempt. Now, the people who, there are still people who are very attracted to modified Newtonian dynamics or extended theories of relativity. They, you talk to them and they say, well, okay, we just haven't figured it out yet, which is a fair statement. Like, okay, it's wrong now, but that's because we haven't found some, like little corner of the theory. We need to make one little tweak that we haven't discovered yet, and we'll be able to solve those problems. Okay. But in 50 years, we have no viable theory of extending beyond our current knowledge of gravity that is able to explain all observations. That leaves, after half a century of trying, it leaves some new component to the universe, some kind of matter that we have not encountered before, that has not appeared in our particle colliders or any of our experiments so far. We call this dark matter. We do not know the identity of dark matter. We do not know what it is made of. But the advantages of dark matter, it's not a great theory, but it's the best we got, which is if you fill up the universe with some component of matter that does not interact with light, hardly if ever interacts with normal matter, that just kind of exists and has gravity, you are able to explain all of these cosmological observations. The same theory that if you fill up a galaxy with dark matter, you make 80% of its mass dark matter, which is enough to explain the motions of stars. That same proportion of matter with that same set of properties also explains all the other cosmological observations. That's what makes it such an intriguing idea and why we think we're probably on the right track with that.
Just finding it.
There's the matter of finding it, which we have no direct observations of dark matter. We have no indirect observations of dark matter. There are some theories that dark matter does rarely, but enough interact with itself and emits some sort of radiation or messes up nuclear reactions in the sun or things like that. We see absolutely no evidence so far of that. So it's not a great idea. I'll be the first to say, I've developed myself theories of dark matter and how it might influence the wider universe and developed simulations and ways to test this. It's not a great idea, but it's the best we got. And it's less bad than the other ideas based on modifying our understanding of gravity.
Right. Okay, and then dark energy?
Dark energy is a huge mystery, even more of a mystery than dark matter. And what we have in the case of dark energy is that the expansion of the universe is accelerating. That's it. The universe is getting bigger and bigger, faster and faster every day. We have no clue why. Again, we have attempted theories of modified gravity say, okay, maybe general relativity just breaks down at these cosmological scales. Maybe the equations need to be tweaked a little. Every time we try to tweak them, we get the wrong answer. If we tweak them just the right way to explain the appearance of dark energy and the behavior of the wider universe, then we take that same theory and apply it to like the solar system or the behavior of clusters. We get the wrong answer. We can't find a single theory that is able to explain all observations at all scales. So we think this is even more of a bad idea than dark matter, that there is some fundamental energy to the universe, something baked into space-time itself, that if you just fill up space-time with energy, it's like background fundamental energy, that does have the right properties to explain all of our observations, but we have no idea what that energy is or how it got there or why it has the strength that it does.
Back we go.
Where were we?
Well, so I was going to then move on, ask you about the vastness of the universe.
The big stuff.
The big stuff. Like how vast the universe is. Because I love those pictures, the Hubble ones and now James Webb, where it shows you a portion of space and there's like little dots and each dot's like a galaxy.
Exactly. And it turns out that portion is like a tiny, tiny little stamp on the sky.
And so what was it? Trillions of galaxies in the observable universe?
In our observable universe, there's somewhere around 2 trillion galaxies, plus or minus a few hundred billion.
Yeah, give or take.
Close enough.
And each one of those has maybe billions of suns?
Hundreds of billions of
suns.
stars. Yes.
Okay, stars. Okay. But the outside the observable universe, it could be how much bigger? Anything, is it, Ethereum?
On the low end, it's maybe a few times our volume, although we suspect on the low end, it's somewhere around 10 to the 50 or 10 to the 60 times wider. And on the high end, it's literally infinite.
Okay. So
we're
going to have to talk about aliens. We have to talk
about aliens.
We have to do a little bit on aliens. Yeah. Where are your thoughts on other civilizations in space, and also whether or not we have been visited by aliens here?
Fair questions, both very, very fair questions. On the aliens existing out there in the universe, we have absolutely no evidence whatsoever for aliens out there. We see no signals. We see no signatures. We see no structures. We got nothing. That said, when I look up at the night sky and I envision the vastness of the universe, or I simulate it in a computer, I recoil in fear at the thought of this being all for us and of us being alone. I cannot let myself sleep at night with that thought.
Same. I'm with you.
So based on no evidence whatsoever and just based on my own feelings, not speaking as a scientist, but just as a guy, as a human being who doesn't want to be alone at night, that I do believe there are other advanced civilizations out there in the universe, other intelligent creatures who are asking the same kinds of questions that we are. Have we been visited? No, I do not believe that we have been visited or contacted by those intelligent creatures.
So all this UAP stuff, you just brush it off as all nonsense.
I don't brush it off.
Okay.
And I don't think it's nonsense. There are a lot of interesting questions when it comes to UAPs, but the key thing to remember is the name. Unidentified. It's okay for something to be unidentified. This is what powers science. Like dark matter, we could call it unidentified cosmological phenomena, UCP, but we just call it dark matter, which is way better name. Not having an identification for something is great and is fine. But when you say it's aliens, if you say, well, I think it's alien civilizations, it's spacecraft itself, it's no longer unidentified. You're not making a claim of non-identification. You're making a positive claim that you know what it is, which is a whole different ball game. When you switch to that, when you say, well, it's one thing to say, I don't know what that fighter pilot saw. I don't know what that radar signature is. That's fine. That's great. That's worth digging into. But when you say it's aliens, you have to bring a lot more to the table to convince someone like me, a scientist. Science, by its nature, is very skeptical, has an incredibly high bar for evidence. You can't just say it's unknown, therefore I think it's aliens. That's not how the train goes in the science world. If you want to say it's aliens, you have to bring something else to the table. You need some other piece of evidence. Like, oh, I think it's aliens because
Okay.
You need to say more. And you can't point to the unidentified or strange features of the observation itself. You need a lot more. And that bar, in my mind and in the minds of the vast majority of scientists, has not been met.
Right. And when we're searching for signs of extraterrestrial life, SETI, and they've been looking for these is exoplanets.
Yeah, exactly.
Yes.
Planets outside the solar system.
Yeah. And often looking for the ones that are in like kind of the Goldilocks zone and based on the conditions of the Earth. Is that because that's the best chance for finding, or are they ignoring the fact that life could exist on other planets into more extreme scenarios that we haven't accepted because we only believe life, or we only know life in our form in this kind of environment, atmosphere, etc.?
Absolutely. And it's funny you mentioned this. I occasionally write opinion essays,
Okay.
And they've appeared in the New York Times and Scientific American and other places. I actually have a piece coming out in Scientific American in the next couple months addressing exactly this. And it's a deliberate choice. One could argue, as I do in the piece, that maybe it's not the most optimal choice, but it is a choice. And the choice has a solid foundation, which is we only know for sure of one kind of life in the universe, which is our kind of life.
Mm-hmm.
That's the only one we know that's guaranteed to exist in at least one place. All other kinds of life are speculative. So we have a choice. If it were allocating our budgets and trying to design observing scenarios and strategies, we have a choice. Do we try to go after all speculative forms of life and really not know what we're looking for or how to be sure that we found it? Or do we narrow in on our kind of life, which is carbon-based being, water as a solvent, living on the surface of a rocky world around a reasonable distance from its parent star? In principle, that really narrows the search space because you're cutting off all the other potential forms of life. But it has the main advantage of we would know it when we see it or smell it or detect it. Because we know what our kind of life does, we know what it looks like, we know how it behaves, we know what it does to planetary atmospheres, we know what it does to planetary surfaces, so we can go look for those signatures, which we call biosignatures, because we would be able to tell it apart from just, non-biological chemical processes. However, this does reduce the places we can look. So we can't just look in the depths of interstellar space or around any random star. We are targeting our hunt for any kind of life, not intelligent life necessarily, but any kind of life around sun-like stars in the Goldilocks zone, having the right distance from the star, looking for watery planets. We're looking for rocky planets. We're looking for ones with substantial atmospheres. This severely cuts down the number of options, but it has the distinct advantage that we know what we're going to see. I don't know, and I don't think that's necessarily the best approach. I think we should invest more time and more effort to exploring different possible varieties of life and what those signatures might look like. I think we should invest. To give you some perspective, the James Webb Space Telescope cost over $10 billion to build and was over a decade late, is a supremely powerful instrument. It will be up to later generations to decide if it was worth the time and money it took to construct it. But for now, it's doing great, getting a lot of science results. It does not have the power to find signs of life in nearby planets. It just doesn't. That will be up to the next generation, the next telescope, something we're calling the Habitable Worlds Observatory.
Is that so? That's already under. That's a project that started.
It's being designed right now. Construction has not begun, but it will be like a super James Webb.
In space, not from here.
It's in space. Yes.
Okay. By the way, the whole James Webb thing, I followed it for years. I read this magazine called Focus. You might know it. I love it. It's like simpleton science for a normie like me. But I was so nervous about the launch of the James Webb because I was like, all this years, 10 billion, whatever, 20 billion they spent of it. If something goes wrong in the takeoff and it blows up.
Or in its deployment, if one mirror doesn't unfold.
Yeah.
Or the sun shield crinkles up on itself.
All this, and I was like, honestly, I was fucking nervous. We're at it.
But that's one of the reasons it was so over budget and delayed was we only had one shot. And so test after test after test after test and verification, validation on the ground to make sure we had the best chances in space, in deployment.
So the Observable World Observatory was that
Habitable Worlds Observatory.
Is it looking? It won't be so strong that it will be able to photograph the planets themselves, but it will be able to tell by certain measurements that what? How would it?
Yes, it is. Its primary science target will be hunting for life on nearby exoplanets that are promising candidates for hosting life. And it will be able to take a picture, but that picture of like the current
won't have a
design,
little alien waving at us.
No, it's the entire planet will fill up 1 pixel.
Yes.
Okay, which is technically a picture, I guess. But it will be able to tell from that little bit of information, it will be powerful enough to detect the presence of elements in the atmospheres of those planets.
Have we discovered anything yet that we believe is very much an Earth-like planet?
Nothing that is quite fit the bill.
Okay.
There's a list of qualities a planet needs to have to be Earth-like. It needs to have pretty much the same size, pretty much the same density, liquid water on its surface, an atmosphere that's not too thin, not too thick. That atmosphere being mostly something neutral like nitrogen, and then having something like carbon dioxide and oxygen, something we know that can play a role in chemical reactions. We don't have that whole list yet. We have found planets. We have found nearly Earth-sized planets, they're usually a little bit bigger than the Earth, around sun-like stars with roughly the right density. Okay, that's 2 check marks, out of 10, but it's more than 0, so we are honing in on this.
Yeah, and if you extrapolate the number of galaxies and the number of stars within the galaxy, mathematically there should be repeat.
Absolutely. So we expect even in the Milky Way galaxy, our Milky Way galaxy is somewhere around 300 billion stars. Just based on very rough numbers of the 5,000 or 6,000 exoplanets that we've discovered so far. From there, you can start to build some estimates of Earth-like planets around sun-like stars. There's something like 5 billion Earths in the Milky Way galaxy.
Okay.
Yeah, 5 billion duplicates of Earth in our own galaxy alone.
Okay. So mathematically, we should be able to find one. And you would then say mathematically, what are the chances of life forming on that planet?
Exactly.
And I believe somebody did like an estimate that could be up to like 100,000 civilizations.
But these are all made up.
Yeah, of course.
It's all made up. Like, yeah, you can estimate. It's easy to make estimates when you're just making up numbers.
Yeah, okay.
There is no realistic estimate of the frequency of life, let alone intelligent life, out there in the universe. There's nothing reliable.
It's a tough concept to get your head around that we might be the only one.
Which is why I don't like it.
I hate it.
I hate it, but that's not based on science. That's not based on evidence. That's just based on feelings.
I've got a few more things. I mean, I've got pages more, but I've got a few more things.
We're on page 2, by the way.
Well, no, actually, we're on 1, 2, 3. Wow. We're on page 4.
Oh, wow. We made a lot of progress.
But I mean, lots was... Yeah.
Do I pass the exam? Do I get my PhD after this?
Dude, man, you are fascinating to me. It's the way you explain things as well. Like, it's fun. It's fun. Your podcast is fun. It's really isn't to listen to. You take people through the steps logically. It's a great show. I recommend it to a lot of people. Okay.
I appreciate that.
Time travel we talked about earlier.
Yeah.
That we know we can go forward in time essentially by going fast.
Or just by doing nothing. Like, remember when we started the show? It was in the past. Yeah. And now it's the present, which back then was in the future. So we have traveled through time.
But I mean traveling through time relative to you.
Yep.
Yeah. Is there any theory about traveling backwards in time?
Yes.
Here we go.
We're going to do it.
We're going to do it. That's what I'm here for. Because I've made some mistakes.
Okay. Unfortunately, and we're at safe space, remember, it doesn't look like we can.
Oh, fuck.
I'm sorry. But here's the thing. And This is once again a case where we're able to come up with ideas in one theory, say general relativity, but then other theories of physics or even statements of logic come in to ruin the party. So general relativity is our description of space-time. So any question you want to ask about movement through space and time has to pass by Einstein. It has to go through general relativity because that is how we understand the relationship between events in space and time. So if you want to ask the question, is it possible to go back in time? You have to start with general relativity because that's who talks about space and time and motion through those. And there are ways in general relativity alone to construct time machines. It is possible. It is possible looking at that theory in isolation. One possibility, and there are a few, I'll give 3 possibilities of ways to construct this. One possibility is that if the universe was rotating, if we happen to live in a rotating universe, you could pick a special path through that rotating universe and end up in your own past. Another possibility is that if you were to construct an infinitely long cylinder, you just got a metal tube and it's infinitely long and you spin it up to be nearly the speed of light, you can follow a very special corkscrew path around that and end up in your own past. Another is through wormholes. If you're able to construct a wormhole, you can take one end of the wormhole and accelerate it, leave the other one standing still. This removes the synchronization of time between the two ends so that you can go in one end and pop out the other in your own past. There is a whole family of solutions in general relativity that construct what we call closed time-like curves, which is a really fancy way of saying a time machine. This is a way of never going faster than the speed of light, always putting one foot in front of the other, and taking a special path where you end up in your own past. General relativity in isolation allows all of these constructions. So the question is, are these closed time-like curves, are these time machines that are allowed by general relativity, are they like black holes where they get to exist in the real universe, where all the other theories of physics say, yeah, that's cool? Or are they like white holes, where they say, yes, just because you can construct it in the theory doesn't mean they actually appear in the physical universe. As far as we can tell, they're more like white holes. But there's a crucial distinction here. Every time we go to construct a time machine in general relativity, something steps in to break it. Like, our universe is not rotating. We've checked. It's not rotating at all. Last time I checked, there are no infinitely long cylinders in the universe. And also, it doesn't look like wormholes can be constructed. Every time you try to build one, they evaporate instantly. Not actually, but in the theory. So every time you try to construct a time machine, something comes in to say, no, you actually can't. But it's not the same thing every time. It's a different reason every time. We have no theory of physics that we can point to that says, this is why time travel into the past is forbidden. We lack that. We have no definitive statement. All we have are a list of possible options, and then each one of those options crossed off for one reason or another, but we have nothing to say it's impossible. That's where we are. Where it appears that time travel into our past is forbidden, but we can't say why, and we can't say for sure.
Okay, wormholes themselves, the theory of wormholes themselves, they aren't necessarily that you would go into the past, right?
In a generic wormhole, no. But if you take one end of the wormhole and accelerate it to high speeds, then that end experiences time dilation while the other end doesn't. And so now you have desynchronized clocks, which means you can go in the other end and end up and travel into the past.
And the theory of wormholes is that you can bend space-time, the piece of pencil through it.
Into a tube.
Into a tube.
Yeah.
But they would immediately collapse on themselves.
Exactly. They're unstable.
But are there theories of ideas where you could make them stable?
Absolutely.
About vast amounts of energy or something? Or other,
not
or
vast
exotic?
amounts of energy. In order to stabilize a wormhole, in order to make that wormhole throat stable so that objects can actually pass down through it, you need negative energy.
Okay.
Or negative mass, which is not a thing. That makes it challenging. We've checked. It appears that all forms of mass and energy in our universe are positive. It's like having a soccer ball that weighs negative 5 kilograms.
Yeah.
That's not a thing. We can't find it. And then if they did exist, it would violate all sorts of things about like conservation of momentum, which we as physicists hold very near and dear to our hearts. It could be wrong, but we've also seen no examples of it. And we don't know how its existence would mesh with everything else we know about the universe. So again, it's one of these things that it's not impossible, but it doesn't seem very likely based on everything we currently know. And so you can't stabilize a wormhole. You can't build a time machine from wormholes.
And so the ideas of traversing from one section of the universe to another is super difficult.
Nature does not like a cheater. You got to do it the slow way.
Yeah. With physics.
Limited by the speed of light.
Yeah.
One step at a time.
So the likelihood that we will, even if we discovered alien life, the likelihood that we would ever meet them.
That's the thing. That's why I don't believe we've ever been contacted. And that's why we have not seen, that's why I believe we have not seen any evidence of aliens yet. There could be thousands of advanced intelligent civilizations in the galaxy right now. But space is huge. It's way bigger. We talk about with ease of like, oh, like just go to another star. Like that's not how it works. It requires an enormous amount of energy. It requires an enormous amount of time. Space is big. Our most powerful radio signals, the ones that could identify us as an intelligent species, the ones that can span the entire globe. By the time you get to our nearest neighbor star, Proxima Centauri, they are so weak you can't tell it apart from the background radiation of the galaxy. That's our most powerful broadcasts. There could be thousands, tens of, maybe even hundreds of thousands of alien civilizations right now, and we can't see them, we can't hear them, we can't detect them. Someday, in the future, over the next few hundred years, we might be able to catch a little signal, a whiff of a signal from some alien civilization. I suspect we will.
We've had some weird things.
Oh,
as well,
absolutely. Yeah. We've had weird things, like the wow signal, which might be it. We don't know the origins of the wow signal, but it never happened again. It never repeated. So maybe it was a singular event like a Death Star blowing up or something. And we caught the little radio blip from the Death Star blowing up, but there was only one Death Star per generation. And so that's it. Maybe it was. I'm not saying it was, but like, yeah, we've caught weird signals. We haven't caught anything that we can definitively say is a clue to an advanced civilization. We have not seen any signals like that. So the way I like to put it is that we are not alone in the universe, but we are effectively alone. We might catch signals, whiffs here and there, but we're not having dinner parties. We're not exchanging, we're not sliding into their DMs. We're just going to be in our own little bubble in our pocket of the galaxy. And that's the end of the show, folks. Go cry yourself to sleep tonight.
I mean, yeah, but it is still it's also fascinating.
It is.
It blows my mind. And then so it just makes me also then go, isn't it, we don't have to really get into this, but isn't it sad that we're wasting so much time on this planet with such stupid shit when this could be just one giant fluke where we're on our own, or, you know, like we have this responsibility to preserve what we have here and not fuck it up.
That's true in many, many different ways. I actually had an essay come out in the New York Times recently about exactly this, about the vastness of the universe, the emptiness of the universe, and what this means. And it means what we call the small stuff, the petty stuff, is actually some of the most important events in the universe. Not in terms of scale or energy or size, but in terms of uniqueness. Like, we are the only place in the universe where art happens, where politics happens, where science happens. We're the only place in the universe that experiences love and loss and longing and curiosity. We're the only known place in the entire cosmos where that kind of beauty and pain and mistakes happen. That's very special. That's very unique. And that's worth thinking about and preserving and remembering and keeping in mind.
Yeah, because we're the only place that we know of that gives the universe meaning.
Exactly.
Because without us, does it exist?
Or does it have meaning without us?
Man, this was everything I wanted it to be and hoped it would be. And
so I didn't break your heart at the end of it.
I mean, the white holes broke my heart.
I'm sorry about that.
I had this
on behalf of the science community, I apologize that white holes are super cool, but also probably don't exist.
I just had this little weird fantasy that there was like these white hole universes that we created where everything was the opposite.
Mm-hmm.
Everything was running the opposite. Everything was just the opposite.
Yeah.
So, the only thing I haven't asked you that I would, what is we've talked about a lot of weird things today.
Oh yeah, we did.
What is the weirdest things that you haven't talked about where you're like, no, this is really fucking weird? What totally weirds you out? Give me a.
What weirds me out all the time is that we are even able to do this. That there are laws of physics that we can discover that apply throughout the universe. It didn't have to be that way. And for millennia, we didn't think there were. We thought what guided the heavens was separate than what we understood here on the surface of the earth. But then we began to discover universal laws. And what weirds me out is that I can write down an equation. I could write down the Friedman equation. And somehow I am describing the evolution of the whole entire universe as a single physical object with a lifetime, with an age, with an expansion rate, with a history, with the contents, that I can do that. That's weird. That's what gets me. That's what, like, when I look at distant stars on a beautiful dark night, and if you've never seen like a pure dark sky, you absolutely need to. It is a transformative experience. And that we can even begin to scratch the surface to understand that is so weird. I sometimes have trouble believing it.
Well, listen, Ask a Spaceman, although it's expanded into your podcast as a...
Well, I've always had the podcast, Ask a Spaceman, askaspaceman.com, where you ask me questions like you just have. I write them down in a list, and then twice a month I pick them randomly to answer. I've been running that that series for 8 years now.
I used to run every day. And so I got into podcasts. First one, I discovered this guy called Rich Roll, who I eventually met, who turned me into a podcaster. Then I found yours. And yours were great because they're like 30, 45 minutes.
Yep, right around there.
Great for a daily jog.
Yeah, sometimes I'll do a series on if I want to dig into a single topic, and I'll do multiple episodes on it.
About 8 years ago is right, because it was about before I started my podcast.
So yeah, there you go.
But the feed's now more than that.
Yeah, so I've had the podcast. I also do other things. I've written 3 books. Those are out now, working on the 4th. I also have my YouTube channel, which I've used to just repeat whatever was on the podcast, and then we had some nice B-roll to put on the YouTube. Recently, I've changed that, and it's starting to look more about the near future evolution of technology. So like not quite futurism where I'm just making stuff up, but like grounded stuff. Like what does the next generation of exploration of the moon look like? What technologies are needed to advance ourselves in astronomy? And this direction is motivated. I'm very privileged to serve as an external advisor to a NASA program called NASA's Innovative Advanced Concepts Program, which is ideas designed to change the possible. So not the next generation of space flight, but what makes space flight and a humanity in space look radically different? What are the foundational technologies and challenges we need to solve right now to make that happen? And
that's a pretty cool role to get.
It's such a cool program. It's a wonderful program. Anyone can apply. If you've got a cool idea, you can apply. It has a 9% acceptance rate, so good luck. But there's funding there to keep fleshing out ideas and to work on them and look for the strengths and weaknesses and challenges in those ideas. And so, motivated by that, I've recently taken my YouTube channel to talking about of things like that. Like something I'm talking about, an episode I wrote on the plane ride here, is using the gravity of the sun to turn it into a telescope 10 million times more powerful than the James Webb, and what it would take to turn the sun into a telescope. Like radical ideas like that. Yeah. Or what would it take to build a sustained presence on the far side of the moon and turn it into a radio observatory? Or what would it take to actually build a habitat on Mars? There are cool ideas like using fungal structures that feed off the Martian soil and sunlight to grow themselves into structures and habitats. There are brilliant people working on these problems, and so highlighting their kind of research is a joy to do.
Very cool. Well, listen, from a random weirdo in England, sending you an email after watching Interstellar with his daughter. She couldn't have. I kind of wanted her to jump school today and come along, but
you should have.
That had its own challenges. Yeah. But from that to replying to my email to flying over here and doing an interview with me, honestly, I can't tell you how much this means to me. It's been everything I could hope and expected. I love your podcast. AskSpaceman.com. People check that out. Look, good luck with everything. I'd like to visit you in the States sometimes.
Absolutely.
Just hang out. But thank you so much.
You are welcome anytime. And it was a sincere pleasure to be on this show.
Amazing. And thank you to everyone for listening and nerding out with us. See you later.